Let me start with a quick scene. When you open an AI app, type a question and answer appears in a second. It feels instant. But behind that instant results, something physical is happening. Computers switch on, they draw electricity, they create heat. Now I want you to connect this to term everyone uses, that is AGI. AGI stands for Artificial General Intelligence, meaning AI that can handle many different tasks, not just one narrow job. Sometimes you will also hear EGI, Enterprise General Intelligence, which is a practical business framing. AI that can reliably help across many office and companies' tasks, different labels, same underlying need. If AI becomes more capable and widely used, it needs more computation power, and more computation, like if it computes more, it needs more electricity. Simple. So today, I'm not debating when AGI arrives. I'm explaining the base layer that affects its scaling. Heat, cooling, power, and the grid. Quick question for you. When you imagine AGI, do you picture servers and power lines? When people say AI is in the cloud is not a mystery place. The cloud is basically data centers. A data center is a real building with rack of servers, networking switches, power system, and cooling systems. Now, why does this matter for AGI or EGI? Because higher capability usually means more training runs, more user requests, and more always on usages. And all of that happen inside data centers. So AGI is not only a research question, it also becomes an infrastructure question. Have you ever seen inside a data center? If not, just imagine a library. Expect every shelf is a machine that needs electricity and cooling 24/7. This slide is the full story as a chain. Let's go step by step. Step first, electricity comes in. Step 2, electricity powers compute. Step 3, compute creates heat. Step 4, heat must be removed by cooling. Step 5, everything depends on the grid, the power grid. The power grid is the full system that brings electricity to a place. Power plants, transmission lines, substations, and local distribution. Now linked to AGI. If AI becomes more general and more useful, we push this chain harder. So the speed of AI scaling depends on how strong this chain is. Like, which step do you think is the easiest to improve quickly? Electricity supply or compute efficiency, cooling, or the grid connection? Comment in section, write in comment sections. This is the key physical idea. Most electricity used for computing ends up as heat. This slide is the full story as a chain. Let's go step by step. Step first, electricity comes in. Step 2, electricity powers compute. Step 3, compute creates heat. Step 4, heat must be removed by cooling. Step 5, everything depends on the grid, the power grid. The power grid is the full system that brings electricity to a place. Power plants, transmission lines, substations, and local distribution. Now linked to AGI. If AI becomes more general and more useful, we push this chain harder. So the speed of AI scaling depends on how strong this chain is. Like, which step do you think is the easiest to improve quickly? Electricity supply or compute efficiency, cooling, or the grid connection? Comment in section, write in comment sections. So think, if cooling fails for 5 minutes in your laptop, you just restart. If cooling fails in a data center, what happens? It can slow down, shut down, and lose expensive uptime. Now we started talking about cooling. So cooling is not nice to have. It's required for performance and reliability. HVAC stands for heating, ventilation, and air condition. Data centers use industrial grade cooling beyond normal office HVAC. So here this slide messages cooling itself uses energy. So the electricity is not only compute, it compute plus cooling. So here AGI link for advanced AI. You often run systems continuously for long hours and cooling reliability becomes a gate. Now, water. Some cooling systems, especially evaporation based designs, use water At large scale, water use can be significant. So this slide mentioned it can be up to millions of gallons per day in certain cases. Important point here, water use depends on the cooling design, the local climate, recycling systems. AGI link here is, if AI infrastructure expands everywhere, it has to fit local resources limits. So site choice and cooling choice becomes strategic. If you are building a new AI data center, would you pick a location with water stress? Probably not. So geography start influencing AI build out. This is bottleneck that turns everything into a race. Electricity might exist in your country, yes, but delivering huge power to one specific location is difficult. You need substations, transformers, transmission lines, permits, and construction. Here a substation is the place where voltage is changed and power is distributed. A transformer changes voltage so electricity can travel a long distance, then safely enter buildings. And grid connection can take years. Even if GPU improves quickly, the grid often expands more slowly. So grid speed can set the pace of scaling. So this slide gives one real world proof point. If it references PGM interconnection, a major power grid operator in the US. PGM's forecast suggests about 32 gigawatts load growth by 2030 and nearly 30 gigawatt from data centers. So a gigawatt we can consider as is a simple large unit power plant for a power plant scale. So don't memorize these numbers, understand the message here in the news. Data centers are becoming one of the biggest new electricity loads. When data centers become major load, AI growth becomes tied to grid planning decisions. If new big load appears quickly, what must grid do? Add capacity, upgrade lines, or manage reliability? Think of it, answer in the comment. Now we simplify everything into 3 levers. So first one is more power, faster grid build out, meaning building generation and grid capacity faster. Second, better compute, performance per watt, meaning get more useful AI work per unit of electricity. This includes better chips, better software efficiency, and better utilization. Third point here is smarter cooling. So if better cooling tech and smarter location choices, we can achieve this. So here is one interactive question. If these 3 levers move fast, advanced AI can scale faster. If they move slowly, scaling slows down, even if model improve. So this is how it connected to AGI. So let's close it with a grounded picture. Whenever you see an AI answer, remember what supports it: data centers, GPUs, electricity, heat removal, cooling, and grid capacity. So yes, AI progress is about better models, but scaling AI, especially AGI or EGI style ambition, also depends on infrastructures. So thanks for watching this video.